All right, so good afternoon, everyone. Today, we are going to cover section 4.3, but before I cover section 4.3, let's have some announcements, which I sent out in an email. Did everybody get my email? Yeah? Okay, good. So, the second exam is going to be 1 week from today. Okay? And it's going to cover basically the second half of chapter 2 up until what we did this past Thursday. So in particular, today's class is not going to be on the exam. And so it's going to go up to and including section 4.2. So that means we need to know, from chapter 4, we need to know how to find critical points, how to use the first and second derivative test to identify local mins and local maxes, and how to find inflection points. Okay, but we're not gonna have global maxes and mins on the test, which is what we're gonna learn today. So that's the exam. It's 1 week from today. This Thursday is going to be a review session. So please bring some questions to the review. So I would try maybe do some of the problems from the practice exam, which I'm going to post later today. Try some of the problems from the notes. Try some of the problems from the homework that you struggled on. And, write down some things that you've been struggling with and bring them to class. And hopefully we can get those cleared up for you. So that's Thursday's class. What else? Oh, as before, you get to use a scientific calculator on the exam, but not a graphing calculator. Anything else? Oh yeah, I'm also gonna post the bulleted list of study items. So hopefully you guys find that helpful in addition to the practice exam. Okay, on quiz 5, it didn't go very well. And part of that was my fault because I made an editing error on the second problem, which made it unsolvable using the techniques that we've learned so far in this class. So sorry about that. But what I decided to do with quiz 5 is the first part of the quiz also didn't go as well as I had hoped. So what I'm gonna do is for the students who were able to solve that problem and get a good score on the quiz, I will treat that as a bonus quiz, by which I mean I will replace your third lowest quiz score by your score on quiz 5. So your 2 lowest quiz scores get dropped. The third lowest, if you beat that score with quiz 5, I'll replace it. Okay, so if you did poorly on quiz 5, you won't be penalized, is the long short of it. Is everyone okay with that? Okay. I had a feeling there wouldn't be any complaints. Okay, so that's quiz 5. Okay, how to study for the exam. I have office hours today. I have office hours on Thursday. Daria is going to be having sessions at the usual time. Did you decide on a review session?
It's definitely going to be on Monday,
okay.
But they didn't get back to me with time and location yet.
Okay, so 2-hour review session with Daria on Monday. Time and location TBD. So that's that. One other resource that I want to make sure that everyone's aware of, okay, is the Math Tutoring Center. So let me show you how to get there. You just Google U of SC Math Tutoring Center. And then you click this link and you can see there's a schedule of tutors. Okay, these people are graduate students in the math department, like myself, who sit in this room, this online room, and wait for students to show up to tutor for free. So 10 a.m. to 3 p.m. Monday through Friday, you should be able to find some time that's going to work for you. All you have to do is click on this link, you type in your name, and you join, and then suddenly I'm in here with Swati, and they're ready to tutor me. Okay, so it's that simple. And they can help you with anything that you need help with in Math 122, okay? So that's another super useful resource if you can't make it to the SI sessions or office hours. All right, So let's start for today. Actually, any questions, any administrative questions before we start? All right. If not, then let's start. So let me go back before I go forward and just review what we've learned so far in Chapter 4. So Chapter 4 has been all about basically minimums and maximums, which we learned have something to do with the derivative, right? And namely, we noticed that when a function reaches a minimum or it reaches a maximum, we notice that the slope of the tangent line, well, the tangent line will be horizontal. And this tells us that since the slope of any horizontal line is 0, it tells us that we expect the slope of the tangent line to be 0. And since the slope of the tangent line is perfectly described by the derivative, we just have to check the places where the derivative is 0, and those might be a spot where we see a local minimum. The only problem was, when we see a local maximum, we get the exact same behavior. So if I just see that the derivative is 0, it doesn't necessarily mean that I have a minimum or a maximum, right? What I have to do is check what's happening a little bit to the left and a little bit to the right, okay? So if the behavior as I move from left to right is that it's decreasing and then afterwards it's increasing, well, that means that we must have hit a minimum. And if we have the opposite behavior, then we must have hit a maximum. Okay, and if we have no change in the sign of the derivative, as in a function such as one that might look like this, right? This might have a, okay, it's hard to see. Why don't I do it like this? If I have a function which looks like this, right? I might have a horizontal tangent line at 0. But since the function went from being decreasing to then being decreasing again, I didn't have a change in the sign of the first derivative. So this is not a maximum or a minimum. Well, we can clearly see visually it's not a max or a min, right? Because we just go straight through it. Okay, so that's what we covered so far. So the points where we found that the derivative was 0 or it didn't exist were points that we called critical points. And critical points were our sort of candidates, which we then check to see whether they're mins or maxes using either the first derivative test or the second derivative test. So the first derivative test is what I've been describing so far. Check the sign of the first derivative close to our point on the left and right. And then the second derivative test was to check the concavity. Because if we have a critical point and the function is concave up at the critical point, then it must be a minimum. Whereas if we have a critical point and the function is concave down at that critical point, then it must also be a maximum. The only problem with the second derivative test was that there were some special circumstances where it would fail to tell us anything, right? Namely, if the second derivative is 0 at the critical point. Okay, so that was minimums and maximums. And then in section 4.2, we talked about inflection points. Now, what were inflection points? Inflection points were points where the second derivative changes sign. So let's quickly look at what's happening here. So when the second derivative changes sign, it's called an inflection point, and we can see it visually on a graph as the place where the concavity changes, right? Because the sign of the second derivative, whether it's positive or negative, tells us whether the function is concave up or concave down, okay? So if we look for places where the concavity switches from, it looks like it switches from being concave down here, and then afterwards we're concave up, right? So in the middle, there was an inflection point. Okay, so the way we checked that was simple. We did the same thing basically as the first derivative test, only we used the second derivative. So what we did was we made a number line, we checked the places where the second derivative is 0, okay, which if you can take a look at this point, the second derivative will be 0 at this point, and then we just check whether the derivative goes from being positive to being negative, or whether it goes from being negative to being positive. If it has one of those two behaviors, then we call it an inflection point because the concavity has changed. However, if we have a point with the second derivative equal to 0, it doesn't have to be an inflection point, right? It could be like x to the fourth, right? Which looks kind of like this, where the second derivative will be 0 at this point, but we're concave up on both sides. So that's a situation where just because the second derivative is 0 doesn't necessarily mean that we have an inflection point. So those were inflection points. And today we're gonna talk about an extension of this theory, basically. So every time we've been talking about maximums and minimums so far, we've been using this adjective local, right? Why do I always say local max and local min instead of just max and min? And well, the answer is because there's a crucial distinction between what we call a local minimum and what we call a global minimum. Okay? And the analogy that I like to think of, okay, to understand the difference between local mins, local maxes, and global mins and global maxes is sports, right? Most people have either played a sport or they know someone who's played a sport or they're aware of the existence of sports, right? So if you have, like, say, if you're the local champion in some kind of sport, right? Say my high school tennis team, we're the state champions, right? That doesn't necessarily mean we're the champions of the world, right? Or of the nation, right? Or of the universe, or whatever, right? So we may have a situation where we have a local maximum, meaning that it's the highest point nearby, right? But it doesn't necessarily mean that it's the highest point in the entire function on the domain which we're going to consider it. Okay, so that's what we're going to talk about today. So let's start by just warming up. We're going to draw a circle, okay, around every local maximum and every local minimum of f. Well, this one looks like a local max. Okay, this one looks like a local min. This one's a local max. This one's a local min. And this one is a local max. Okay. Now, the definition of a global minimum, okay, is we have a global minimum at the point P if the function is less than or equal to all other values of f on the interval AB. Okay, so whenever we're talking about global mins or global maximums, we will specify the border, basically. Okay, we will specify the border of where we are going to consider this function. Okay? So, it needs to be the smallest possible value of the function on the entire interval. Okay, so where do we think we're going to have a local minimum or a global minimum for this function? Say 1, 2, 3, 4, 5. What do we think for a global min? Probably 2, right? Okay. Sorry, I don't mean to insult your intelligence, but this is basically what we're doing, is we're just looking for the smallest possible value, right? So, the crucial thing that I want to describe here is that this one here that I'm pointing out with the green pointer, it is a local minimum, but it is not a global minimum for the function. Okay, so this is the crucial difference between local and global minimum. Okay, and so this one's a local, this one's a global, min, and the global max is up here, right? Meaning that there's no other points on the function in between a and b which are higher than that one. Okay, so that's the pretty simple idea that we're going to talk about today. So we want to find all the local maxima and minima for this function, g of x, here, and then later we're gonna ask ourselves, okay, how about the global mins and global maxes? So this will just be a pure review from section 4.1. So we have a function, it's a cubic function, and we want to find the local maxes and the local mins. Well, the first step to this is always to take derivative and set it equal to 0. Okay, so the first thing I'm going to do is take the derivative of this guy. G prime of x is going to be 3x squared minus 18x minus 48, okay? And the first thing I'm going to acknowledge is that g of x is a polynomial, which means I don't need to worry about what? Exactly, I think I heard it. I don't need to worry about g prime not existing. G prime of x always exists. So, I know that I will have a critical point at any location where the derivative is either 0 or doesn't exist. I've verified already that it always exists, so I just need to check the places where it might be 0. So I set this equation equal to 0. All I have to do to solve this is divide by 3 on both sides. This tells me that x squared minus 6x minus 16 is equal to 0. And if I want to find the values of x which make this 0, I can do it in one of two ways. I can use the quadratic formula, or I can factor. I'm going to factor this time, since this one's an easy one, I think. I just do minus 8 and plus 2, I think, right? What you want is for these two numbers to add up to the middle one, and if you multiply them together, you should get the last one, right? That's how we factor. So if I take two numbers and I multiply them together and I get 0, then that means that one of them has to be 0, right? So either x minus 8 equals 0, which tells us that x would be 8, or x plus 2 is equal to 0, which would tell us that x is equal to negative 2. So I found the values for which x is equal to 0. Now, I'm going to classify them. Sorry, is there a question? Oh, I think I just heard somebody sawing something. Okay, so I'm going to put them on a number line and use, well, I'll do the first derivative test this time. So if I do the first derivative test, what do I need to put on here? I put negative 2 and I put 8. And to do the first derivative test, I just need to pick a test point from each sub-interval. So I need to pick one to the left of negative 2. The easiest one is probably negative 3. And then I'll pick one which is in between. How about 0? That one's easy to plug in. And one to the right of 8. Why don't I just do 10? 10 should be simple. Okay, so all I need to do now is plug these in to the derivative and see what I get. So g prime of negative 3 will be okay, g prime of negative 3 is going to be 9 times 3 is 27 minus, Jesus, okay, I'm going to use 18 times 3. Why is my calculator not working? 18 times negative 3 is going to be a plus 54, and then we're going to do minus 48. And what we need to do is check whether this number is positive or negative. Well, this number is clearly positive, since I take two things which are, well, one of them is already bigger than 48, right? So this is going to be positive. So I have derivative is larger than 0 here. Okay, what happens if I plug in 0? G prime of 0 is just going to be negative 48, which is something which is less than 0. So the derivative is less than 0 in the middle region. Why did I put that there? And then at 10, what am I going to get? I'm going to get 300 minus 180 minus 48 is going to be something larger than 0 again. Okay, so I see that the derivative goes from being positive to then being negative to then being positive. So the general shape of this function is that it's going to be increasing, and then it's going to be decreasing, and then it's going to be increasing again. So that tells me that I'm going to have a local maximum at x equals negative 2 and a local minimum at x equals 8. Right? It's going up, and then it's going down, and then it's going up again. So the function has a local max at x equals 2, negative 2, and it has a local min at x equals positive 8. So this is how I did this one using the first derivative test. Do we want to see how to do it with the second derivative test too? Yeah, okay, why don't we show how to do it with the second derivative test. So let's say you don't vibe with the number line and the plugging. So let's do something else. Let's use the second derivative test. So this is still this part. Second derivative test. What do? We take the second derivative, g double prime of x. Well, it's going to be 6x, right? Because 2 times 3 is 6. The power goes down by 1. Minus 18, right? And now all I need to do is check, is g double prime of negative 2 larger than or less than or equal to 0? That's what I want to check. So I do g double prime of negative 2. If I plug in negative 2, I get negative 12 minus 18, which is definitely less than 0, which tells us that the function is concave down. G is concave down at x equals negative 2. If our function is concave down, then that means it corresponds to a local max. Okay, likewise, I need to check. How about x equals to 8? Well, g double prime of 8 is 6 times 8 is 48 minus 18 is 30, which is positive. So our function g is concave up at x equals to 8, which tells us that we get a local minimum. Okay, hard to see that. Sorry. So that's the basic principle behind the second derivative test. So I think the second derivative test is a little bit easier for this one. But that's because it kind of works out. You always run the risk of not getting anything out of the second derivative test, which doesn't mean that there's no local max or local min. It just means we need to go back and use the first derivative test. Okay, any questions about finding local mins and maxes using the first and second derivative test? Yeah?
Where does 6x minus 18 come from?
So 6x minus 18 is the second derivative of g. So the original function was x cubed minus 9x squared minus 48x, right? So I took its derivative and I got 3x squared minus 18x minus 48 equal. And so if I take the derivative of that function, then I get g double prime, which is 6x minus 18.
Okay.
Christian?
For like our exam, would you ask us to do like for one problem, say solve for the mins and maxes using the first test and one, using the second test, or could I like just focus on one for my study?
You can definitely just focus on one for your study, but if you focus on only one, it has to be the first derivative test, because the second one sometimes doesn't work. So yeah, if I will not ask a question on the exam where I say solve it using this particular method.
Okay.
You can use any method of your choice as long as it works and is mathematically viable. Yeah.
If g double prime of x is 0 for, like, what would that actually look like? Wouldn't it be, like, how would that be a min or a max?
Well, it looks like this.
Okay.
The function f of x equals x to the fourth. So we did this one. We took its first derivative. We got this guy, right? And so we said this guy is going to be 0 when x is 0, right? And so, if I want to check whether x equals 0 is a min or a max, all I have to do is take the second derivative and plug in 0, right? Well, if I take the second derivative and plug in 0, what do I get? 0 again. So it doesn't tell me anything. It doesn't tell me whether the function's concave up or concave down. It's because the function happens to flatten out at this point. So we don't get anything out of that second derivative test. So this is the situation where it can fail, is basically if you have a function the function's derivative and its second derivative share a root. Okay. Any other questions about this first example? Yeah.
So for testing out critical points, is it better to use values that are farther apart or closer together to the critical point?
Well, what you need to make sure is that the value that you pick for the question is, how do I choose which points to plug in, right? Okay. The first thing that we need to do is we need to make sure that the points that we pick are in between each interval, okay? So I need to pick a number which is less than 8 and bigger than -2 for the middle interval. Beyond that, the only thing that I like to do for choosing the test points is I like to choose points that are easy to plug in. So why did I choose 0 instead of 7? Well, it's because I'm going to need to, if I choose 7, I have to plug it into this thing, and I'm going to have to do 3 times 49, and that's annoying. I don't want to do 3 times 49. I'd much rather do 3 times 0. 3 times 0 is my favorite type of calculation to do. So that's why I picked 0. So I like picking whole numbers if I can, and I like picking numbers which are going to be easy to plug in to the second derivative, or the first derivative, right? So I picked 10 instead of 9 because it's easier to do 3 times 100 than it is to do 3 times 81. That's the only reason. Any other questions on this one? These are all great questions, by the way.
And is it true that when you plug in some values, you'll get like the same results? So like if you plug in, like I did 7 and 9, I still got that both answers were greater than 0. So that suggests that the function somewhere took a dip when it should have gone up, or vice versa.
Well, we found the 2 points where the derivative is 0, okay? So in between, the derivative can't switch from being positive to negative anywhere in between, because if it does, it would have to be 0 at some point, right? So I know that the derivative's all or nothing. It's either positive in this interval and in the entire interval, or it's negative in the entire interval. So is that what you were asking? Okay. Any other questions? Okay, let's move on then, because I have some stuff I want to get through at the end of this class. So let's just talk about the difference between local maxes and local mins. So I found a local max and I found a local minimum. And now we're going to change the question, okay? Now we're going to talk about the function g on the interval from -5 to 14. Okay? So we're going to graph the function. And we're going to ask ourselves, are the local maximum and minimum that we found, okay, x equals -2 and x equals to 8, are those also the global maximum and minimum of the function on this interval? So let's take a look at the function on the interval and ask ourselves, okay, our 2 points, right, where this was -2, right, and then we had 8, right? So this is where we got our min, our local min, and our local max. So the question is x equals -2 the global maximum of this function on the interval from -5 to 14? Someone said no. Who said no? Shania says no. Why not? Yeah. So the answer is no, it's not a global maximum, because there are points elsewhere in the interval where the function is taller than that. Namely these points here, right? At all of those points there, the function's taller. So this is a local maximum, but it's not a global maximum. Okay? How about the local minimum down here? Do we think this one is a global minimum? Yeah, this one is a global minimum. But this one is not a global max. Okay, so this raises the question. Oops. Based on our observations in problem 3, we want to complete the list of places where we might look for a global maximum or a global minimum. Okay? So we already have these two from before, right? These ones are the places where we find a local max or a local min. So they're a natural place to check. Okay, are those places global maxes and global mins? But there might be some other places that we want to look. So let's just ask ourselves, if this one isn't the global max, where is the global max? Well, it looks like the global max is all the way over here. Okay? Yeah?
How would you tell though that 14, or the point at 14 is a local max if that function is cut off at that point? Or is it necessarily
Well, it's not necessarily going to be a local max, right? Because we wouldn't be able to check what's happening to on the right side if it, right? Is that your question?
Yeah, I was wondering though how you could tell from the picture like where the point is that it was a global max, because you can't see the entire function, or you can't see the entire curve at that point.
Right, but we can tell that there is a point right here, right? And we can see that of the part of the graph which we can see, do you agree with me that this is the highest point that there is? So that's how I can tell that it's a global max. Because if I go left and right, there's no points which are above it in this interval. So does that answer your question? Yeah, so that's how I can tell that it's a global maximum. So how can we finish the list? The places where I might find a global maximum are maybe the places where I find a local max, and maybe where else? Sorry? The borders, or the boundary. Yeah, exactly. The boundary of the interval, okay? So, the question is, where might I find the global maximum or global minimum of a function on the interval a comma b? I need to check the critical points and also a and b, the points on the boundary. X equals a and x equals b. Those are the places where I need to look for a global maximum. Okay. So, if I have a problem like this one, problem 2, okay, and it asks me find the global max and global min of this function on the interval from -5 to 14, the first step is to find the critical points, classify them as local maxes and local mins. Then finally, what do? We make a table. So to finish global max and min search, make a table. And on the table, we are going to put the x values on one side and the function values on the other side. And the values which need to go here are all critical points plus a and b. Okay, so on here would go -2 and 8 because these are my critical points. And I'm also going to include the boundaries, which in this case are -5 and 14. And then what I am going to do is find the value of the function at each of these points. I know that the global max has to occur at one of these points. So I just check the heights for each of them, and I check which number is the biggest and the smallest. So then check for biggest and smallest number. Okay, so in this case, I'd take -2, I'd plug it into the function, see what I get, I'd put it here, and then I'd take 8, I'd plug it into the function, see what I get, I would put it here, I'd take -5, plug it into the function, see what I get, put it here, and I'd take 14, plug it into the function, see what I get, and put it here. And I would say, aha, the one with the 14, that's the biggest number, so it's the global max. And then I would say, for the 8, this one, I'm going to get the smallest number, meaning the most negative in this particular circumstance. So that's the global min. Yeah, Christian.
Could you not also use this method just with your critical points to find the local maximum instead of like taking points along the number line?
Oh, I see what you mean.
Like you take your
Yeah, so
your 8 and you plug them into the original function, and whichever one's the bigger and the smaller one. Or like say you're like a 0 in there as well.
sure.
You know what I mean?
Yeah. The only problem is, let's say we use your method and I have a function which looks like this, i.e. I have 2 local maxes, right? If I make my table, okay, one of them's at 5 and one of them's at 8, right? Let's say that. If I make my table, and here's x2 and this one's x1, right? If I have x1 and x2, I get, okay, respectively 8 and 5, right? When I plug them into the function. But this tells me nothing about the fact that even though this one is smaller than this one, it's only telling me that x2 cannot be a global max. But it doesn't tell me that x2 is not a local max. In fact, it is a local max.
I thought x1 was the local max.
x1 and x2 are both local maximums because for a point to be a local maximum, it just has to be the highest point in a subregion of the graph. Okay? It's like if I return to the roller coaster analogy, right? There might be 2 peaks on the roller coaster. But the question is, what is the highest peak? Well, this one is the highest peak, but it doesn't mean that this one is not itself a peak.
Okay.
This is the difference between global versus local. Right? It's the highest, local means it's the highest point in a region if I restrict my vision to a smaller subset of the domain.
Okay.
How do you know where to draw the boundaries of a function?
How do I know where to draw the boundaries of the function? It will always be given in the problem. It will always say on the interval from something to something. Yeah.
So for the table, do you plug in the numbers in the original equation, the first derivative or the second derivative?
Original equation in this case, because in this case, when we're asking about the global maximum or global maximum or global minimum, right? This is a statement about the height of the function, right? So we want to check where is the height the biggest. The function which tells me the height of the function, right? That's just the function itself, right? Its derivative would tell me the slope. Second derivative would tell me the concavity, right? But in this case, I'm checking the function itself. So yeah, I can see where you're coming from, that it's confusing how sometimes when we do the first derivative, we're taking critical points and we're plugging them into the derivative, right? Or the second derivative test, we're taking these critical points and we're plugging them into the second derivative. And now I'm telling you, when we're doing global maxes, you take these critical points and you plug them into the function itself. So there's all sorts of these different things, and it can be difficult to keep it straight. But it just takes a little practice, okay? All right. Any other questions? Okay, no more questions. Then maybe we'll do one more example. Okay, we'll do problem 5. I wasn't planning on doing this problem, but we'll go ahead and do it just to see one all the way through. Okay, so I'm going to go through this example nice and slowly, and then after that, I'm going to spend some time reviewing the chain rule, because I think we should go back over that a little bit. So, they tell us that there's a bird, and the bird expends a certain amount of energy each day. And that depends on how long does the bird spend on that day foraging for food. Okay, so we plug in an amount of time in a day that the bird spent searching for food, and the output of the function is the amount of energy that it used. Okay, foraging for a shorter time requires better territory, which then requires more energy for defense. Oh, okay, so this is just a statement, I guess, about the shape of the function. So, find the foraging time that minimizes the energy expenditure if E of t is equal to this function here. Okay? Sounds simple enough. So really what we're trying to do is take this function and find the global minimum on TBD. So the first step is we are looking for a global minimum of this function. First, we want to find all the critical points of E, okay? We want to find all the critical points, because anywhere there might be a local min could be a place where we might have the global min. But we're going to check it, right? So let's start by finding the critical points of this function. Well, the critical points are, of course, going to be e prime of t is going to be the derivative of this function, so let's just take that. It's going to be 0.25, right, because the t becomes t to the 0, which is 1, and then plus 1.7 over t cubed times negative 2, okay, because this is 1.7 t squared to the negative 2, sorry. So when I bring the power down, it becomes this negative 2, and then I make the power 1 less than it was before, so it becomes negative 3, which means it looks like a t cubed in the denominator. Okay, so this is my e prime of t. Okay, and I check for the critical points, right? The critical points are well, I set this equation equal to 0. So if I do that, I get 0.25 plus minus 3.4 over t cubed is equal to 0. So let's just go ahead and solve that. We get 0.25 equals positive 3.4 over t cubed. Multiply both sides by t cubed. We get 0.25 t cubed equals 3.4. So we divide both sides by 0.25, and we get t cubed equals, dividing by 0.25 is the same as multiplying by 4. So 3.4 times 4, we get 13.6. And to finally get t, we take the cube root of this. So we take 13.6 to the 1/3 power, and we get 2.39, roughly. Oh, why don't I say 2.3? 2.387. Okay, so 2.387 is my only critical point. And now our next step is, okay, to consider what are the endpoints of the interval, right? Because a global min is going to either occur at a critical point or at an endpoint. So what is the least and greatest value of t that would make sense in this problem? Well, I think that the bird is going to have to spend some amount of time foraging for food. So why don't we say, okay, this is a sort of a flawed problem. I'm going to add the qualifier up here. Assume minimum 1 hour spent foraging. I wouldn't give a question like this on an exam because it's too vague. But let's assume that it spends 1 hour minimum foraging, right? Then we just need to consider the endpoints are going to be the largest and smallest values of t, which makes sense in terms of the problem. Now, t is an amount of time in a day that a bird spends foraging. So if the minimum is 1 hour, then what's the maximum amount of time a bird could spend foraging in a day? Yeah, 24 hours, I guess, if it doesn't sleep at all. Okay, so I think those are our endpoints. So we're looking for the global minimum of this function on the interval from 1 to 24. Okay, so based on the list we made in problem 4, we want to write down all the values of t where we might find the global minimum of the function. Well, we know that the global minimum is going to occur at either a critical point or a boundary point. So I'm going to make a table with t values, and on here I'm going to put 1 hour, that's the minimum boundary point, and I'm also going to put my critical point, which I found, which is 2.387, and I'm also going to put the maximum, which is 24. So I know that this function is going to reach a global minimum at one of these 3 points. So I just check, what do I get when I plug those numbers into e of t? Well, if I plug in 1, I get 0.25 plus, sorry, what do I get? I get 0.25 plus 1.7, which would be 1.95. Okay, how about if I plug in 2.387? Then I'm going to get 0.25 times 2.387 plus 1.7 over 2.387 squared, right? So let's multiply this times 0.25. We get, roughly speaking, 0.59 plus 1.7 divided by parentheses 2.387's quantity squared. Enter 0.29, 0.30 actually. So okay, I take these numbers and I add them together and I get 0.89, right? And finally, if I plug in 24, I get 0.25 times 24 is 6 plus I'm going to have to take 1.7 divided by 24 squared. 1.7 divided by quantity 24 squared. So I get 6 plus like 0.003, which is 6.003. Okay, so now I have my table of values. I have the 3 locations where I might find a global minimum, and I found the value of the function at each of those points. So where am I going to have a global minimum for this function? Yeah, the minimum energy expenditure is when the bird spends 2.387 hours foraging, right? Because the number on the right is the energy expenditure, and it's the smallest, so that's the global min. Okay. So you'll notice, by the way, that in order to do this, I didn't actually verify initially that the critical point was a local minimum, right? I didn't verify that the critical point was a local minimum because all I need to do is, I know it's a critical point, which means that maybe it's a local min, maybe it's a local max. But in any case, if I plot all the critical points and all of the boundary points here, I know that the minimum is going to be among the right-hand side. So I just look for the smallest number, and hey presto, I've got my global minimum. Yeah?
If you had more critical points, like say you had like 2 or 3, would you then have to verify which ones are the local mins and maxes?
No, I would just have to put them also in this table, and I'd get more numbers here and here and here and here, right?
Okay.
But all I'm doing here is checking what is the smallest number among these guys. Good question. Any other questions, Brendan?
How would you know that like another number for T wouldn't end up giving you an even smaller one than 0.89?
Okay, so that's a great question. So the question is, how do I know that this one's the minimum and there isn't some other minimum at like 4.5 hours, say? Can anyone answer that question? How do I know that there's no other minimums smaller than this? Yep.
Because you checked the smallest boundary. Like,
Well,
there's no other critical point in between the smallest boundary and the
Exactly. I know that if the function has a global minimum, it will occur at either a critical point or a boundary point. Since I found all of the critical points, there was only one critical point, I checked what is the value at that critical point, and I checked the value of the function at the endpoints of the interval. And I found out that this was the smallest one. If there was another point which was smaller than this, then it would be a critical point. So local minimum implies critical point, but critical point does not imply local minimum. I just check all the critical points and all the boundaries, and I look for the smallest one, and I know that the minimum cannot possibly occur anywhere else. More question?
What do the global minimums and maximums mean in terms of this problem?
Like how to interpret it?
Yeah.
Okay, so yeah, this one has a very real interpretation, right? The function e, where did I go? Okay, the function e here, right? What does it tell us? I plug in a number t and it tells me the amount of energy that's expended. So in this particular circumstance, it's telling me the way to interpret this, so the interpretation is the minimum amount of energy the bird can expend occurs if the bird forages for 2.387 hours. This is the interpretation, right? So the minimum height, since the height of the function is telling me how much energy we expended, if we find the minimum height, it's the minimum amount of energy. Good question. Any other questions on this one?
Wouldn't it make more sense for it to have expended less energy if it only did the minimum amount of time foraging?
Well, yeah, I guess that's what this statement here is is supposed to catch, I guess. It says foraging for a shorter time requires better territory, which requires more energy for defense.
Okay.
So if the bird is only spending an hour foraging for its food each day, it must have really good territory, so it has to fight off all the other birds, and so it's spending energy that way instead. So it's like a optimization thing. It's like I want to have territory that's good enough that I don't have to spend too much time foraging, but I also want to not have the best possible territory such that everybody else is always pestering me. So if you think about it, based on these numbers, right, the function probably looks something like this, right? So lots of energy if I have a good territory. Then there's an equilibrium point, right? And then if I have really shitty territory, then I have to spend a lot of energy looking for food. Okay, so that's just all I wanted to say about this example. The point is, find the critical points, find the boundary values, plug them into the function, and see what you get. The biggest number is the global max, the smallest number is the global min. All right. For the rest of class, I wanted to go back because I think there was some confusion about the chain rule. So I'm going off script here for a bit, and we're just going to go back and take another look at some chain rule practice, okay? So chain rule and product rule and quotient rule and all of the other derivative rules, you'll see when I post the bulleted list later, they're under this category which I put on there called non-negotiables, okay? Which means things that are absolutely critical for you to know for the exam. And what we need to make sure we know how to do is we need to have the rule memorized, and we need to know how to apply it and when to apply it. Okay, that's what we're going for each and every one of these rules. But I think chain rule is the one that I'm noticing students are struggling with the most, so that's the one I'm going to talk about today. So, if I have a composition of functions, okay, which means I have one function inside of another function. In this case, it's the function g of x is being plugged in as the input in the function f, right? So I'm combining two functions by plugging one into another. And if I take the derivative of this combination, of this composition, then what am I going to get on the right-hand side? Who can tell me what the rule says I'm going to get? F prime of g of x.
Is it plus or times?
It's times
Times
g prime of x. Okay. If you were not sure about what to put into this blank, then it's like mission critical to resolve that as fast as possible, because this is going to be like very necessary for the exam. So if you're feeling behind on this, that's okay. It just means you need to get some help from me or Daria or the Math Tutoring Center, okay? So it's not something that can't be resolved. It's just I'm trying to communicate the importance of it, okay? So this is what the chain rule says. Now let's see how we actually use it. Okay, so the way that I tell that I need to use the chain rule is when I see one function being plugged into another function. Okay, so that can look like a variety of things. It can look like a situation where I have a function which is then being raised to a power, okay? Or it might look a little simpler. It might literally be like one function which is literally inside of another function like this. Okay, or it could also be when we have a function in a power. That's another common situation, is when we have a function which is in the power, right? Let's see, any other situations? Oh yeah, sometimes we even have functions inside functions inside functions, right? So this is an example of a double composition. So there's three functions here. The innermost function is this guy, which is then being plugged into the function which is this guy, which is then the power in the outermost function, okay? So I look for things like this, where I see functions inside functions, and that's my cue. I'm gonna need to use the chain rule for this problem. So let's start with the first one. If I wanna apply the rule, okay, I wanna identify what is the innermost function and what is the outermost function, okay? So, there's two ways of doing this. Like I said when we covered chain rule, the first way is to literally write out what is f of x and what is g of x, okay? And then find their derivatives, f prime of x and g prime of x, and then literally plug in using this formula. That's one way to do it. But after you get a lot of practice with the chain rule, you probably won't write all of that out every time. So I will show you both methods really quickly on this first problem, and then we'll work together to do the other ones. So the first way I would do this would be to say, well, this is a composition of functions. I know I need to use the chain rule, and the first thing I would be doing on my paper is writing down this statement. That would be the first thing that I would do on this problem. And then I would write, so which one's the inner function and which one's the outer function? Well, in this case, the inner function is the one that's inside the parentheses, right? So my g of x is going to be x squared plus 3x plus 17, and then my f of x is going to be or f of z is usually what we did. We use a different letter for f, is going to be z to the 52nd power, right? So if I take this whole function, g, and I plug it in for z in this function, then I get my composition. So this is a breakdown of the composition. And now it's as simple as applying this formula, because I chose my functions in such a way that although I don't know how to find the derivative of this guy, I do know how to find the derivative of each of these two pieces individually. So g prime of x is 2x plus 3, and f prime of z is 52 times z to the 51. So if I want to figure out what the derivative of the composition is, all I need to do is apply this formula, which says take regular g of x, so that's x squared plus 3x plus 17, and plug it in for z in the function f prime of z. That's the first part. So what does it look like? It looks like 52 times x squared plus 3x plus 17 times to the 51st power. Then multiply by the derivative of g. So the derivative of g is 2x plus 3. If I'm going to plug it into this equation, I need to remember that I always plug with parentheses. So I multiply by 2x plus 3 with parentheses. And now I'm done with this first problem. Okay, so first step. I can tell I need to use the chain rule because I have a function inside of another function. Second step, I know that this is the formula for the chain rule. Third step, identify the inside and outside functions. Fourth step, take their derivatives. Fifth step, plug them into the formula. How do we feel about that? Is that one okay? All right. So let me briefly comment on how you might do this after you have a bit more familiarity with the chain rule, right? What an very observant person might notice is that this guy is nothing but the derivative of what's inside, right? So if I'm going to do a chain rule like this, I probably wouldn't write out all of this jazz. Probably what I would do is just recognize that this is a composition of functions, and I can see that the inside function is this x squared plus 3x plus 17. And I know the first part of the chain rule is always just to leave the inside alone and just focus on doing the derivative of the outer function, right? Which the outer function is just this 52nd power, right? So the first thing I do is I leave this part alone, and I just bring the 52 down and I subtract 1 from it. Then I have to multiply times whatever the derivative of this inner part is. Okay? So that's the sort of faster way of doing it. Any questions on the first problem? All right, let's look at the second problem. Question for the class. Do I need to use chain rule to do the derivative of ln of x? Yes. Why do I need to use this chain rule? Yeah, the cue, right, is that I have a function inside of another function. Composition. Okay, so what's the inner function? What? Yeah, g of x in this case is ln of x. And how about f of z then? It's ln of z. Okay, now what is g prime of x? Sorry? Not quite. 1 over x, right? And f prime of z, how about that? Yeah, 1 over z. Okay. So now that I have my inner and my outer function, let's put it all together. Let's start with the first part. F prime of g of x. What do I get? One over ln of x. Am I done? No, now I need to multiply by 1 over x. And I get 1 over x ln x. Okay? So that's how I do that one. So you'll notice, again, the form here, I can see that the inside function is ln x. So if I wanted to skip to the end, what would I do? I would recognize that the inner function is just going to be left alone while I sort of do the derivative of the outermost function. So I do just 1 over whatever's inside, right? 1 over whatever's inside, which is ln of x. And then what do I need to do? I just need to take whatever was inside and multiply by its derivative on the back end. Okay, so I just take ln x, I multiply by its derivative. Yep.
If we left it as 1 over ln of x times 1 over x.
That's fine. Yeah, you can just leave it like this if you want. As long as your answer is, as long as you've done the actual work of the problem, I don't care if your answer is like equivalent to the real answer. Okay, let's do another one. Okay, this one's tricky. I've got e to the 3x to the 16 minus x squared. Do I need to use the chain rule on this problem? Yes. Why do I need to use the chain rule? Yeah, multiple functions. What are the two functions that I've got here? I think I heard someone say that this one in the power, that's going to be one function, right? That's the sort of inside, right? It's inside in the sense that it's inside of the exponent, right? So what is my g of x going to be? It's going to be 3x to the 16 minus x squared, the whole power. Now, what is f of z then? E to the z. Okay, so g prime of x is 48x squared, no, sorry, 48x to the 15th minus 2x. And how about f prime of z? E to the z. So, I'm not going to put the formula on the screen. What do I do? What's the first step to writing down this derivative? F prime of g of x. So I take regular g and I plug it in to f prime of z. So if I do that, I get e to the 3x to the 16th minus x squared. And am I done? No, what do I need to do now? Multiply by g prime. Okay, so 48x to the 15th minus 2x. All good? Yeah. Very observant. I need parentheses when I multiply by g prime. Okay? If I don't put these here, then all I'm doing is I'm multiplying this times this and then subtracting 2x. I don't want to do that. I want to take this guy and multiply it by this guy. So I need my parentheses so that I remember to distribute if I were to simplify this. Very good. Okay, any questions on that one? All right, let's do another example. Uh-oh. Uh-oh. What's scary about this one? Three functions. Function inside of functions inside of functions. It's like that old show. What the hell was it called? Pimp Your Ride. Remember the exhibit memes where he would be like, I heard that you like cars, so I put a car in your car so you can drive while you drive. That's what we're doing. Okay, maybe I'm just like too old now. You guys remember like Exhibit and Pimp My Ride, right? Come on. Okay, good. Okay. So that's what we're gonna do. We're just gonna do a chain rule inside a chain rule. Okay, so I'm gonna do this the quote unquote fast way. Okay, I'm gonna play a little fast and loose here by just recognizing first. I'm just gonna treat this as the quote inside. Am I running out of time? Oh, I have 4 minutes. This is the inside, and I'm gonna treat e to the z as the outside. And what would I do if I did that? What I would do is I would do just whatever, I'm gonna leave this part alone and do the derivative of e to the z. Well, the derivative of e to the z is just itself. So the first part of this is just to rewrite. This is my f prime of g of x. Now what do I need to multiply by? I need to multiply by the derivative of this function. So, to do the derivative of this one, I know that the outer function is the 20th power, right? And the inner function is the 3x 16 minus x squared. So to do its derivative, first I copy this, 3x to the 16 minus x squared, all to the 20th power. And now I'm gonna write the derivative of that guy, which I have to do this derivative using the chain rule again. So when I do its derivative, I get 20 times what was inside before, I don't change that part, to the 19th power. And am I done? What do I still have left to do? I still need to multiply times the derivative of this guy. So I multiply now by 48x squared. Sorry, 48x to the 15th. I don't know why I keep saying that. Minus 2x. Now am I done? Yeah, now I'm done, right? Because to do this derivative, I didn't need to use any more chain rules. So it was sort of like the bottom of the bucket. Yeah.
Will you have like the function within a function within a function on the exam? Or will it just be like the normal one, which is 0?
I can't say. Maybe. But it's something that you should know how to do. So, you know, if you were going to do this in terms of your f and g and h, so let me just show you how it would work. If you have f of g of h of x, if you want to just memorize this rule because you're scared of triple chain rule, then this is the way it goes. Its derivative will be f prime of, we leave the inside alone, g of h of x. Now what I need to do is multiply by the derivative of g of h of x, which is done by using the chain rule. It's g prime of h of x times h prime of x. So if you have a triple chain rule problem and you want to memorize this formula instead, then that's another way you could do it. And in this case, you just need to identify what is f, what is g, what is h. For our particular problem, we had that h of x would have been the innermost 3x to the 16 minus x squared. g of z would have been z to the 20th, and f of y would have been e to the y. All right, so I'll post this on the Blackboard. That's it for today. We'll have a review session on Thursday. Please come prepared with questions. I hope you found the review for chain rule useful. It's going to be pretty important to know that for the exam, so figured I'd spend some time on it.
Can I take the quiz now?
Sorry?
Can I take that quiz now?
Quiz 5?
Yeah.
Why don't we do that
That's fine.
next time?
Okay.
Can you come before class on Thursday?
Yes, I can.
Okay, let's do that.
Cool, thanks.
I just have a quick question.
Sure
on
thing.
how you found the derivative of this? Because I thought it'd be quotient rule. Doesn't say that.
Okay, so the reason you don't need to use quotient rule on this one is because the top is a constant.
Oh, okay. just
So
go back, basically.
in this case, you can rewrite this as, you can rewrite it as 1.7 times t to the negative 2. If you write it like this, you use the constant multiple rule, the 1.7 is just going to hang out.
Got it.
And then to do the derivative of t to the minus 2, you do,
Even though the negative 3
the power would become negative 3, and you'd multiply by
by negative 2?
negative 2. Yeah, exactly. You multiply the power down and make the power 1 less.
Oh, okay, because I was just confused on how we, like, it went straight to that. Okay, I get it now. Then. Thank you.
Yeah, no problem.